Hey, how's everyone doing? It is right before spring recess. If you're in the chat, feel free to say hi. We're going to wake up Mewbot right here. Mewbot, where are you at? He's not awake today, but we're going to wake him up. He's just going to crash the world behind us. We're going to clear out R. We were doing some time series earlier. We'll see. Is Kayla here? I know Kayla was asking. Who all is here? Hey, Nick. Good to see you, Nick. 100 points. Appreciate you being here. We'll put on a little music in the background here, and we'll get started here. You know, we're going to play one of our favorite songs that we don't play so often. The space music. Sierra, great to see you. Brandon, great to see you. You know what? Let's just throw out a crazy 1,000 points. You guys give me that energy, 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 as BTS once said. Come to Stats1 for your BTS references. Oh, did I just delete the wrong chat? I didn't. There we go. I'm not... Oh, cool, Nick. Anytime. Nick, we're glad to have you. Always glad to see you here, Nick. Thank you so much. Are you in A3? I'm trying to remember. My brain's booting up. Are you in A320? Are you 201? Nick, we're just, hey, you want to be here? You want to practice? Learn some new material? That's what we do. I'm going to learn some new material. You get to see some cool new techniques. 479, then you're reviewing. I was like, Nick, I swear you've been here. We got to give you another 1,000 points. Everyone, I want some shout outs in the chat here to Nick. Nick, you've been one of my students. The problem is teaching online, I don't see people in person. I was like, I know Nick. Nick, congratulations. We got to do this here, Nick. This is for you. Just give a second, right? Give big shout outs. This is going to be for you, Nick. I got to fix this. Give a second here. All right, here we go. All right. 2 seconds. Are you ready? It was for 320, 201, 475, 474. Awesome. Dr. Lou is amazing. Okay, you ready, Nick? Let's see if I fix this. This is shout outs to Nick right here. We got to turn off the music for this. Nick, this is special for you. You ready, man? Here we go. I've made a mistake on my I don't move across the screen anymore. I'm gonna have to look at my hotkeys. The hotkeys got unbinded, so I'm supposed to move across the stream when I'm like. Mid dab. Oh, mid dab. Sad times. Get serious here. Oh, Nick, congratulations and awesome work. Just really excited, really honored. Today's a big, crazy day for me. If you didn't see it, maybe I should post. Maybe I'll put it on my classes and stuff. But did they put it over here yet? Oh, they already. Wow, it's already on my page. They were quick on that. You know, yeah, I'm okay with that picture of me. But really quick, big day for me right here. Some big news. The Brian Stevens Business Analytics Award for Business Analytics Student of the Year has been established, and I got to speak to Nick. Nick Brown was one of the first recipients of the Milton Scholar Award, and so Nick Brown right there, amazing student. Nick Brown, well, he's not a student anymore, but if I could have given him this award, I don't give it to him. Thank you so much, Brandon, right there. So really crazy, big news, and thank you for everyone being here. Thank you for Nick working so hard. We're not stealing Nick's thunder here. Nick's getting all those points. Congratulations, Nick. We want to share the good news with everybody when we get it. So a little bit of good news from me, a little bit of good news from you. Nick, congratulations. I have my MSBA, and let me just tell you, it's an amazing degree. So great work, and thank you. So Nick, we're just glad to have you here. Hang out, man. Yeah, that's all the Nicks. Oh, yeah, it's another Nick. So, yeah, LinkedIn. Where's Nicholas Brown on LinkedIn? I've got like a crazy amount of notifications right now on LinkedIn. There it is, Nick Brown. Nick Brown on LinkedIn back here. So this is Nick Brown right here on LinkedIn. I guess I don't have a ridiculous amount. I got to go look. But that's Nick right there. Associate Director of Data Science at S&P Global. Let's do some activities. You got it. And we're going to do that here in a second. You got it. 4.0 from UT. But Nick has done an amazing job. Really honored to know Nick. So shouts to all the Nicks right there. Let's do some activities. I agree. It is time for activities. Okay, so here we go. Over to the main screen. Let's do this. Okay, we're going to take a timestamp right here. It is 6:50. Start, or question 1. So with this question right here, what do we have? Part A, data EX9 birth weight, and save it as baby. Oh, it did it for us. What fun is that? Okay, so what we have right here is data that's preloaded into R. Now tell me, why when you type OS does this not show up? I just want you to understand what the data function is doing. Why when you type all this OS stuff does it not show up? I bet Nick knows, or bet Brendan, do you know? 100 points on the line right here. Why when you type OS, now it probably doesn't if you're in 320. If you're in 475, it probably will show up. Take a look over there on the side, and what does the data function do? Hey, Caleb, good to see you here. Awesome, Caleb, Nick. We got so much great news today. This is data that's like pre-installed programs almost. So these are data sets that we are kind of pulling from R's preloaded data sets. And you have to have these packages right here. So the reason you have the EX birth weight is because what package is EX birth weight in? EX birth weight, and just take a look what it's showing you right there. The reason you have access to it and you can load it up when you do this is that the EX birth weight was in the what data frame? Not the data frame, library, correct wording. The EX9 data set is in the what library? It says it right over there. So it's in the what library? The reg class Sierra, exactly. And that's how in 100 Point Sierra, great work. That's when you type in the OS, you don't get all the OS production stuff, the OS accommodation, the OS passengers, all this good stuff right here. You don't have these, or you could if you get the FPP3 library. You will have it installed, our package is FPP3. We're not here to do that today, but we're going to make a baby data set. By doing that, we're just storing right here baby, and this is just creating a copy. You want more babies? More babies. That's how we do it. This is how we make them. We just make duplicates. The reason you might make a duplicate is because you might start to change your data frame. If you're going to change your data frame, you might want to make a copy of it because there's no undo button inside of R. So think about making a copy of it. If you have a data frame, you kind of want to work with it and then alter it. We don't need all that. We just need one. One's enough. One baby's enough. So with this right here, we have the data set, and we're going to look at the birth weights of babies. Shocking news right here. These are mothers, and the birth weight of their baby is, I think, here in grams. What is 3,118 grams in pounds?
That would be 6.87 pounds.
Whoa. So this baby right here is 6.87 pounds. That's not a big baby, right? The biggest baby in this data set is 5,000 grams. What is 5,000 grams to pounds?
That would be 11.02 pounds.
That's a pretty big baby. That's an 11-pound baby. I don't know what grams are. What is 1,560 grams to pounds?
It's 3.44 pounds.
Whoa. Tell me about this. Talk to me. We're trying to understand our data right here. All yours were 6 pounds? That's a little small, right? Congratulations, Kayla, right there. So 11 pounds a lot for a baby, right? I think I was closer to 9.6 or something. It said that baby right there is 3.44 pounds. That baby's 3.44. We're trying to understand this data before we use it. So what's the deal with that? 3.44 is like, woo! I mean, that is probably pretty premature, which could be a preemie. And we can look at the gestation. This is the number of weeks. So if we times that by 7, the length of their pregnancy was 204 days. How many days long is the usual pregnancy?
Here's what I found from healthline.com.
280, it says. So that's pretty premature. Like 204 divided by 30. Yeah, 40 weeks. Yeah, so they went 6.8 months, and 40 weeks is going to be, I don't know this. So that's a pretty short pregnancy right there. And we have all this information on the mothers, the fathers, and an important variable over here at the end is smoking. As Jim Carrey once said, smoking. Smoking has 2 levels. Are you smoking now or never? Kind of a weird way to ask the question. It's the only way the question asked. Do you smoke now or have you never smoked? It's kind of no in between. You either are smoking now, currently, or you've never smoked. So, first question here is, what is the reference level? Now, it's important we know when we talk about reference levels, what kind of variables have reference levels? When we talk about reference levels, what is a variable that would have a reference level? If a variable has a reference level, I think we'll see. If a variable has a reference level, which this does, the reference level is the one that is first what? And it's for categorical variables. So the reference level will be the one that is first what? You see it right here. We have the note also coming up here in a second. There it is. The reference level is for categorical x's. So take a note on that. The reference level is for categorical x's, and it is the one that is first alphabetically, as you can see there with freshmen, sophomores, juniors, and seniors. So it's the first. It's the first one alphabetically. So if we look at it and we say, okay, there's two levels to this. Finding the reference level for this, whether it be now or never, is a simple question of which one is what. So what would we do here to find this? The reference level is definitely what? And so what is it now? How will we find it? The reference level is definitely this because it's this. So there's only two levels. The two levels are now and never. So if we look at the variable, it doesn't have like smoking, not smoking. It just says now or never. So it says now or never. Correct. The reference level will be never, because never is first alphabetically. And then we will see a indicator variable for smoking now. And I can show this real quick here. So though you are correct, I want to show this here because that's what you're thinking, and that is correct. So if I make a model predicting because this is what we're going to do here in a second. If I make a model predicting the birth weight of a baby, and I do it from smoking, is literally the next question. The reason we don't see birth weight. What? We want to do that? Sure, we'll attach the data set. Then I get the autocomplete. There we go. What did I have wrong? Oh, it's a lowercase w. Wow, that's hard to see. It's a lowercase w. That's very hard to see. That's oof. The reference level is when all indicators are set to 0. Good questions, Kayla, 100 points. The reference level would be when all indicators are set to 0. So the only way someone's a freshman is if they're not a sophomore, not a junior, not a senior. Does that make sense? The reference level, if there's multiple levels of indicators, the reference level is when all indicators are zeros. So if you're not a sophomore, not a junior, not a senior, you are a freshman. Just like with this model right here, which is a very small model, the only thing in here is smoking now. And this also confirms our answer. Who's following with me on this, that you don't see the reference level? Because the way the reference is found is that somebody is, and this is the indicator right here. And think about what this means. This might literally be the next question. Oh, so yeah, I think this is. Okay, let's do the next question instead here, because I think we have it. Okay, so let's see if this is the next question. Let me put a point in here. So the reference level is the one we don't see, and it's the one we make comparisons to. And here we'll start up question number 2. Question 2. Yep, I think you're on the right track. I think you're on the right track with this. So fit a simple linear regression predicting birth weight in grams from smoking, only smoking, the coefficient of smoking, exactly. So when you look at this right here, what does this mean? Well, we can actually write out the model. Let's take a moment here and write the implicit lines. And they'd actually be 2 naive models. Unfortunately, it won't graph for us. But think about how this model would look. Kayla, can you write the model predicting a birth weight of the babies right here? Like if we write the model for Sierra and Brendan and Nick, if you want to join in, can we make a model predicting birth weight is equal to what? Birth weight is equal to what? Think about, remember, it's just this plus this times this plus this times this. There's not much to this one, though. So how would this be written? It's birth weight equals this plus this times this plus this times this. So what is it? What do we have when we write this model? And then we'll see what it means. So what would we get? we need to first start with the intercept, and then we'll add on to it the coefficient of the smoking now and the variable smoking now. So what would we have here? Remember, it's just birth weight equals, you can see this is birth weight, that's the y variable. This plus this times this. Yep, Kayla, that's got it. Great work. That is it. And so we just drop that in here. We take this and you need to do minus. Great work, carrying the minus because it is a negative coefficient. And then let's see if we can make sense of this. Think about what this coefficient means. The coefficient is smoking now. Smoking now can only take on two values. Great job, Sierra, right there. Smoking now can only become a what or what because it's an indicator variable. Hence, indicator variables have the variable name at the start. Here's the variable name. Then they have the level they indicate for that variable after them. Notice how this is an indicator variable. And it can only become 0 or 1. Exactly, Kayla. Since it can only become 0 or 1, we put a 1 when the mother says, I am what? So if I put a 1 here, boop, that would mean what? If I put a 1 there, that means what? So if I put a 1, that would mean, oh, you are. Think what it means because we put a 1 for this. You are smoking now. I have indicated, the mother says, I am smoking now. Let's say I can see that. And so this means the predicted birth weight of a mother who is smoking now, because it's a yes to that question, would be what comparatively to a mother who's never smoked? The predicted birth weight of the baby of a mother who is smoking now would be what to a mother who has never smoked? And we can see it mathematically here because this is what it'll solve to. The predicted birth weight of a baby for a mother who is smoking now would be what to a mother who has never smoked? And think about what the coefficient means, because that's what the coefficient is telling us. So the predicted birth weight of a baby for a mother who is smoking now is expected to be, or two mothers, we don't say is otherwise identical, but two mothers where one who is smoking now and one who is smoking never. The mother who is smoking now, the predicted birth weight of their baby is expected to be what? And then that's what the coefficient is telling us. Exactly. We not positively correlated, but this coefficient tells us, and great job, Sierra, right there, and good practice. This coefficient right here tells us that the predicted birth weight of a mother who is smoking now, comparatively to a mother who is smoking never, we'd expect the difference between those two mothers to be a difference in birth weights of their babies of 271.77 pounds, where the mother who's smoking now is expected to have a baby that weighs less. Does that make sense? So two mothers who are otherwise identical. It's not a multiple yet. Will be soon. The mother who is smoking now is expected to have a baby that weighs 271 pounds less. Because we just said, oh, yes, you are smoking. If they're not smoking, you'd plug a 0 in, and then literally, I mean, here's the not smoking model. That's the I am not smoking, and there's no other things. And here's the I am smoking model. So there's nothing else for these models, just a flat line. It's like that's the predicted birth weights for mothers who are never smoke. That's the predicted birth weight of babies for mothers who are smoking now. Question 2B. Run associate, and we're going to see this right here. So this is the same function, just kind of showing you some overlap between the techniques you're doing. And what do you notice? Do you remember that coefficient we saw a moment ago? How much was that coefficient? Well, I bet you I can find it again. Now, this doesn't do it to the decimal, but that coefficient we just saw a moment ago right here is the difference between the what's. Look what I just did. Look at the values I did and say, oh, that's the difference between the what's of the two groups, which is what this is estimating. So we're actually seeing the difference between the what's of the two groups with this model right here when it does the indicator variables. So what is it doing right here? It's actually finding the difference in the means. Exactly, Kayla, because that's the mean of the never smoking. That's the mean of the now. And this difference, it carries a little more decimals right there. Darren, we're going to put a little lag in the chat. Darren's messing with our internet again. The difference of 271.77 is what we see between the means. So, you know, it's kind of the naive model for both groups to say, let's predict the average for the mothers who smoke now and the average for the mothers who smoke never, and predict along those groups right there. 2C. Is the overall difference in average between birth weight smokers and non-smoking mothers statistic? Oh, yeah. Is it statistically significant? I laugh. Kaylee, I don't get what. I don't get. Oh, it's a joke in the afternoon class that Darren's messing with the internet. It's an afternoon class joke. Whenever people put lag in the chat when there's a lag, so we made Mewbot say stop messing with the internet, or Darren's, because someone joked it's Darren messing with our internet, and so we put that message in whenever someone says lag. So Mewbot just jokes Darren stop messing with our internet. That Darren's like caused the problem. It just it makes me laugh and stuff. Has like little inside jokes. So is this statistically significant? That is a question I hope we're like, is that statistically significant? If that's on the test, you're like, oh, free question. So for statistical significance, we always look at p-value. And this is the associate function, but we could go up here and look at the model p-value or the intercept or the slope p-value, excuse me. Yes, Kale, 100 points. You are correct. Both the simple regression show a p-value of significance on the x variable of interest, and the model itself, which is the same p-value. Additionally, the associate function looking at the difference between the means shows statistical significance. But then we have to ask, is this difference important? And I don't usually speak in grams. But tell me, Kayla, is a difference of more than half a pound a practical significance in difference in baby weights? If they said to you, your baby's going to weigh 0.6 pounds more, is that like, I mean, would you be like, whatever? Oh, that's a good. I mean, if I gain 0.6 pounds in a day, I probably just ate a cheeseburger. But for a baby, newborn baby, does that sound maybe practically? Well, it depends though, right? Because if we're talking premature, and like if someone's like 5 pounds, that's a lot of their weight right there. Like a 0.6 of a pound. Like for babies, there might be, like if the average baby weights of this group, what if I told you it was a whole pound? Like these babies differ by a whole pound, 1 pound. And they're like, like yeah, baby group A and baby group B differ by a pound. That's a pretty big difference between baby groups. And I said, well, these mothers smoke and these mothers don't smoke. And maybe Kayla, 100 points. Maybe I should listen to you. I've had no babies. But the 0.6 difference here is attributed. Ounces? No, that's 0.6 pounds right there. So that'd be 0.6 ounces. How many ounces would that be? That'd be 16 ounces in a pound, right? So that would be like 9 or 10 ounces. That'd be like 10 ounces. Something, right? I think because 16-ounce steak is a pound, right? So that'd be about 10 ounces, I believe. Double check my math. There you go. About 10 ounces. This is out of my knowledge base. Brendan, this is business analytics right here. We have to do the baby mathematics. So, I think this could be, that's a lot for a baby. 10 ounces makes a big difference. Bingo, Kayla. That's what I was thinking once again. So that's about 10 ounces on a baby right there. And that's a pretty big difference right there if you see differences between groups of 10 ounces. And if this is attributed to smoking now versus smoking never, maybe something's going on. Question 3, lurking variable time. Question 3, lurking variables. The observed difference in birth weights could be smoking. Could be. But it could be other variables. For example, it could be the case that mothers who smoke tend to have shorter gestation periods. Like, imagine this. Would a mother who, like a mother, let's say, has her baby at 30 weeks, a mother has her baby at 40 weeks. Would you be shocked if the mother who smoked and had a baby at 30 weeks is, I'm going to do this every time I smoke. It could be other factors, right? So maybe it's how long they were pregnant for. And doesn't it make sense the longer you're pregnant, the bigger the baby? I mean, that makes sense. Like mother's pregnant for 8 months, smaller baby, mother pregnant for 10 months. Whew, bigger baby. So maybe it's other models. Maybe it's other variables. So how do we do this? Well, in multiple regression, what do we need to do? If someone says, maybe it's this variable, what do you do? If someone says, I think I got a lurking variable for you right here, what do? Someone's like, this variable? I think it's the real variable. So what do? You say, okay, you say variable? You say, what do? So you got a variable for me? You got a variable? You say, add it to the model. You say, okay. Well, let's just take my model here. You say you got a cool variable for me. Great job, Sierra, right there. Boop. You say you got a cool variable? Well, let's just add it into the model. Boop. I have run the attach function. If you're wondering why I'm getting the autocomplete, You have to attach the data frame to get autocompletes. That attaches, great job, Brendan and Kayla right there. So the reason I can get them to autocomplete is I've run the attach function, which attaches all vectors to the global environment. It can cause what's called masking, where things have kind of repeat names. But this kind of helps with any typo errors. It's very nice. Petrie, it's not a big fan of it. Tuning in from a different stats class. Jonathan, great to see you here. Are you 201, 320? Are you UT, not UT? We're glad to have you. 100 points, Jonathan. So here is the model now with more variables included. Now, these variables have kind of joined into the octagon. And so we're big fans here of everybody, Jonathan. These variables have joined into the octagon to work together to see if they can help or if one of them comes out victorious. And it turns out, is smoking still significant? Yes or no? What are your thoughts? Is smoking still significant? And how do you know? And then what does that mean? Is smoking still significant? It is. It definitely. Yeah. Oh, yeah. It's still super significant. And what does that mean? It means exactly the p-value. That means that variable brings with it what? Say the two-word phrase that starts with something and ends with information. It means that, mathematically it reduces the sums of squares in a significant way when it's added to the model. That's why it's mathematically significant. But that means it's explaining variation unaccounted for by the other variables, meaning it's explaining something information about the model. 3-letter word, something girl. Surely someone knows about that show. It's explaining new information. New Girl was the show. So it explains new information right there. I always have my big thing that I figured out a long time ago is I always try to have students say the answer. If you say it, it helps you remember it better. So I love when you're typing there in the chat and remembering those answers. Because if I say it, it's one thing. But if you have to write it or say it, you remember it a little bit better. So it's new information is what the low p-value means, is that this is helping in a significant way, not attributed to the other variables. We could look at things like the variance inflation factor. I don't know if this question goes into this, but there's not much multi-collinearity there. Yeah, my fiance. Hey, Alexander, great to see you here. My fiance is a big fan of New Girl. Zoe Deschanel, you rock. So right here, gestation highly explains it, and smoking highly explains it, and they work together in a good way. They're both significant, bringing with them new information. There's not an overlap of multi-collinearity between the variables. And now, what is this model going to look like? This model visually will look how? It's important to understand. I used to have students draw it, and I think they said, why, Brian, this is not an art class. But you should know what it's about to look like when we do this. And Alexander, I think my R's working again. We should look at the 3D plot at the end of this. I'll probably have to... Stat1's about to start their test, and that's... it's been a crazy day. What will this model look like when I create it? Who knows what the model will look like? So I have a categorical variable and I have a quantitative variable. This is indicator regression. Indicator regression is when each level gets its own line. Careful. How many levels are there to the categorical variable? Careful. How many levels are there to the categorical variable? Be careful. How many levels are there to the categorical variable? I wish it would, Brendan. That'd be cool. How many levels are there to the categorical variable? 2. Correct, because you do not see this the reference level. The reference level is smoking never, and you don't see that. So when we run this, and the reference level will always be the black line, the way this is coded. So here's the smoking never. I'm going to show you 2 mothers here. And I'd like you to tell me, in terms of gestation period, these 2 mothers right here, in terms of gestation period, we'll do them in a blue color. In terms of gestation period, these 2 mothers are what? In terms of gestation period, these 2 mothers are what? So here, I'll put it towards the center so we can be a little bit better when I zoom in. In terms of gestation period, those 2 mothers are what? I did as best I could to make it look like that. They're supposed to overlap. How would you describe their gestation period? The gestation periods of these 2 mothers are what? They're the same. They're identical. You mean these are 2 mothers who are otherwise identical, but one of them is smoking now and the other has never smoked? These are two mothers who are otherwise identical, but one is smoking now and one is smoking never. And these two mothers, I would expect them to differ in the birth weight of their babies by what? These two mothers who are otherwise identical, where one is smoking now, like they're otherwise identical, but one is smoking now and one has never smoked. The mother who's smoking now, I'd expect the birth weight of her baby to be 241 grams less than the mother who has never smoked. So once again, make sure to reference the picture because it literally shows you two mothers who are otherwise identical, i.e. they have the same gestation, but one is smoking now and one is smoking never. The expected difference in the birth weights of their babies is 241 grams. We also have the gestation period telling us two mothers who are otherwise identical but differ in their gestation period by 1 week. The mother who has a longer gestation period is expected to have a birth weight of a baby that is 91.273 grams more. Know how to do your interpretations. Yeah, Shazad, feel free to ask. Feel free to ask. What is the NP again? So no worries. NP is the success failure condition. N is the amount of trial or the observations, and P is the true proportion. Chapter 13, sampling distribution of sample proportion. Thank you, Cezanne. 100 points. Thank you for asking. And the summary of the model. Oh, we got to write some models right here. So who feels like writing these models are easy? I know things, I got to stop saying things are easy, but it's just this plus this times this plus this times this. So let's try writing it. Are you ready? How do we write the equation? I want you to help me write the overall equation. So remember, it's this plus this times this plus this times this. So start, we'll write birth weight, which is the y variable of interest. Birth weight equals this plus this times this times this times this. What do we have? Just go through the output and do it algorithmically. Remember, the intercept does not have a x with it. Write the first model, and then the next ones are easy. What do we have? We'll take a second right here. Try to do this at home. Be able to write these. Just try writing on a sheet of paper. Stat 1 test starts in 35 minutes. That is correct. To check the success failure condition, it is the sample size times the population proportion. That is correct. And then NQ also, because we need to check both NP and NQ greater than 10. Great job, Shazad. Birth weight, I think, Kayla, I think you got it. I want to go on a limb here, and I think you're right, Kayla. Please know what Kayla did is we just have intercept plus this times this plus this times this. I swear there are test questions like this. Now we can solve for how many lines with this. Just put in the chat, how many lines is Brian going to solve for? Look at the screen for your answer. How many lines is Brian going to solve for? That's the full equation. We're just going to go here and put in a 1 for smoking now. And we're going to take from negative this and subtract. Please reduce these when you find them. There's that line. So this is the line right here. That is the intercept for it. It's not hit on there. Great job, Alexander. And then we're just going to take... oh, the other one's easy. If they're smoking now... Check this out. You ready? Just put a 0 in. And it's gone. That's it. That's all the lines right there. These are the two lines you see on the screen. The difference between their intercepts is the difference in intercepts of the coefficient negative 241.46. And that's that difference right there. Hopefully, does it make... Who has questions on how I wrote these? Is everyone good on the writing of the equations? You want to find the overall equation first, and then from there, solve by putting in the indicator where you indicate they're either smoking now by a 1 or not smoking never by a 0, because that's the reference level. It's the one you don't see. If there was multiple indicators, you would need to put in multiple zeros to get to the reference level for all the indicators. Only one indicator for a variable can be on, and something like day of the week would have 6 indicators, with Friday being the reference level. But hopefully, slow me down if you have questions, let me know. And I know a lot of people use these videos, especially later. Jonathan might be from another university, or who knows what, might be from one of ours. Here we go. Where to go? Good stuff. Is one always going to be? Yes. You never put in like a 2 or anything. it's always because it indicates the 1 indicates it's like a binary operator, Kayla. So the 1 is always a yes to it, and the 0 is always a no response to the indicator. So if you put a 1 in, that indicates that they are that value, that level for the variable. Great questions, Kayla. That is correct. Only 1s or 0s there. Only 1s or 0s. So when you do indicators. Hey, Troy, what's up? 2 things I ran for the 201 exam and finally reached. Oh, nice job, Troy. We threw out some crazy points. Troy, thank you so much. And Troy, you got this. Good luck, Troy. Great work, Troy. Good luck. You got this, Troy. And we're so proud of you. Crazy points here. I think Kayla is going to try to... There's some point competitions going on. We gotta make some new levels. I need to figure out a good way to standardize my points. Thank you, Kale. All the positivity. We're always here to cheer each other on. Vols help Vols, and Vols cheer for Vols. Finding the predictors that is most correlated with birth weights and gestation, using all correlations, fit the linear regression, predicting birth weight from smoking, and these variables. Oh, wait, what? Wait. The variable. Okay, determine the variable. Yeah, all correlation. Okay, we're going to find the variable most. I keep busting the roof on him. I know, right? Oh, Kayla. Yeah. Yeah, competition right there. Love it. Oh, Kayla, you're about to hit 200,000 too. You probably hit tonight's stream. Great job. And great job, Alexander, right there. So we're going to run baby, interest, with birth weight. Make it look pretty. And sorted equals magnitude. Okay, I got it. The variable most correlated with birth weight outside of gestation, besides gestation, is what? The variable most correlated with the birth weight. I guess that makes sense. The variable most correlated with birth weight outside gestation. Which makes sense. I'm on a sleepover break. Is what? The variable most correlated, which is logical. Thank you, Troy. Keep rooting for everyone right there. The variable most correlated with birth weight outside of gestation is what? Because I've sorted this, so it's easy. Well, gestation is the most correlated. Yeah, gestation, right there. Yep. The variable most correlated outside of gestation is mother height. So taller women generally have, and like we could look at this relationship. We could plot. I bet we could do it now. Birth weight. Wow. That's got a correlation. Wow.
Wow.
Shocker. That looks very weak. Okay. Fit a model predicting birth weight from the predictor and smoking. So now we're just coding it from that predictor alone. Fit the linear model predicting birth weight from smoking and this variable. Okay. That's easy enough. So let's go grab our model. And we're going to see if it can do a better job. Basically, we've been hired by a tobacco agency to talk about pre-game the exam. Good to see you, Dylan. 100 points. We've been hired by a tobacco agency because people are saying tobacco is not good for babies, and I agree. But we've been hired by them to research this, and it's not turning out so good for them. So does it look like smoking is still significant? So you're hearing some 201 tobacco. Does it look like smoking is still significant in explaining? Does it look like smoking is still significant in explaining birth? It is. It is. It still brings with it new information unaccounted for by the other variables. Mother's height is significant, like how tall a mother is. If we wanted, we could always just add in gestation. Something tells me we're still going to... The problem doesn't ask us to do this, but still smoking is very significant. Really, smoking is... And if you're in 201... for 500 points, and I will throw 1,000 if a 201er answers it first. Who could interpret the R squared of this? Interpret the R squared of this model. Remember, predicting birth weight. This is related to your exam, 201. I mean, you're not doing multiple regression, but it's not too different. When you hear it for 320 right here, you'll be like, oh, it's just that? That's all it is? We'll give them like 30 seconds right here. You got it, 201ers. Take a. I'll honor a good shot at it. If you get most of it, I'll give the 1,000. If you get a good shot, I'll give a 500. So what do we do to r squared? Let me put the hints on the screen from earlier. Here's our documents. We're almost done. We're almost there. Okay, good. Here's the help for it. Remember predicting birth weight. So we're predicting birth weight. Oh, Kayla. I'm throwing the 1,000, Kayla. We'll see if they answer, but 24.78% of the variation in birth weight is explained by the variables. I would count that. Troy, you're starting at 1,000. Why not? Troy, I would count that on a 320 test. I would just say the variables in the model. I'd say close enough. If you said variables in the model, I'd do 100% because the model. So Kayla, somebody out there, 24.7% of the variation in birth weight is explained by the, yeah, exactly, by the X's, by the variables in the model. Great job, Troy. Because it's just the model now. It's just there's X's. Does that make sense? 24.78% of the variation in birth weight is explained by the variation in, you can say the model or the variables in the model. But it's just, yeah, the variables in the model. You could list them if you want, but you don't have to. I mean, you can. There's nothing wrong with it. Great job, Alexander, right there. So Troy, great practice. And if you notice, this relates to our 201 topics of regression. This is what is called multiple regression. And they're actually kind of breaking the rules of QQ. But Kayla, why is it not really breaking QQ? Because this categorical variable can only, when it comes to indicators, can only take on what levels? You got this, Troy. Bully that exam. Throw some dirt in its eye. Bully McGuire it. This indicator variable can only take on zeros or ones. So even though it's categorical, we're using a trick to turn it into something that works. All the references. It just looks like different numbers. No, it's still smoking. Now predict the birth weight from all the variables in the data set. Remember to use the twiddle dot. We're just going to grab our code. We cannot actually visualize this. It just doesn't work for visuals. Okay, let's put all variables in. Oh my gosh. Oof. Whee! Okay. Wow. The R squared, this in Alexander, the indicator changes the intercept exactly. The intercept is a constant change on the intercept. And these are all the variables in the model. And so if you notice, there's probably some multicollinearity here. I probably bet there's some multicollinearity. What? Oh, VIF is capital. Ooh. Wow, that's interesting. Don't worry about the GVIF over here. The highest collinearity in this probably is due to what? Which, I don't know if I ever ran it on this. Which, think about, now, collinearity is the shared variation between two variables. Multicollinearity, which VIF measures, is the shared variation between one X and the other X's. Oh, yeah. The indicator can... Ooh. Alexander... That's worth some 500 points. Good stuff. Good mnemonic memorization. What do you notice right here where the multicollinearity is probably mostly coming from? I used the first one, the GVIF, which is the generalized variance inflation factor. It's still VIF. It just has to calculate it differently because of the categorical X. Where do you think a lot of the overlap in shared variation is coming from? A lot of the overlap is probably due to what? Probably due to what in this data set? Like, look at the two large numbers. Right there. Probably due to a lot of collinearity between that. We go look at the data and we look at... where's mother race? There's mother's race. White, Asian, white. Black. Do you notice? What do you notice about this? This is the race of the mother. This is the race of the father. And why do you think we're seeing a lot of this right here? Because I really am having a hard time finding. Does this make sense in the race? Up. Look at that. There. Finally. I'm not seeing anything. White. I'm not seeing anything else. And what do you? Oh, wait. No. Well, really? Is that the only one? I could do a search on it. What do you notice right here about mother's race and father's race of a baby? What do you notice about mother's race? I could write a code to just look for it. What do you notice about mother's race and father's race? Actually, it's a really easy code to write. baby, mother race equals baby, father race. There's that. Take mean 95% of the time. 95% of the time. That's the code for it right there. 95% of the time, the mother and the father in this data set had the same race. Does that make sense? Yeah, exactly. And that's probably causing a lot of the variance inflation. The variables are basically the same. Does that make sense? Variance inflation is when our x's bring redundant information. So if I told you, let's just take a random baby here. I'm going to tell me a number between 1 and 553. Tell me a number between 1 and 553. So someone in the chat put a number between 1 and 553. And this is what variance inflation is. So 1 and 553. Tell me a number between 1 and 553. 499, of course. Okay, this baby, their mother is white. And I bet the father is white also. I would bet good money. Blah, 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 blah. It's the computer doesn't want me to do it. I'd bet good money right here. Let's take a look. Here we go. Boop. There you go. Look at that right there. Boop. Yep. So that is confirmation. 420. And so that baby, their parent is also white. Their mother's also white. And I bet their father's white. And their father's white. So that's because it's basically redundant information. That's what multicollinearity is. So kind of a review of what multicollinearity is. Now, this technically is collinearity because I'm just talking about two x's. Kayla and Alexander, does that make sense why I'm talking about a collinear relationship? This x with another x basically explain each other, where multicollinearity is how is one x explained by all the x's. This gets into matrix algebra with matrix reduction and linear independence of vectors. That's not my building. And the question is probably of a new marketing thing here. That at least one is it. Yeah. How's the answer? 1 minus probability of all failures. Given past success. So 1 minus, probably I think is 0.7 and 2D. Is it 5 campaigns? I think that'd be it right there, Shazad. I think that's it. Why did I do? Because 1 minus all failures. Probability of failure, 0.7. And then 1 minus all failures. Yeah, no, I'm going to go check on him soon here. Yeah, no, I gave him some critical. Thank you, Alexander. 100 points. I appreciate that. He's getting some critical care, I think. Probably need to feed him again. Bunny. Chelsea's better at feeding him. I'll help Chelsea here soon. Thank you, Alexander. Yeah. Now predict. The coefficient splitting tells the difference between otherwise comparable mothers. What is the difference in average birth weight between otherwise identical mothers? So where would I look in the output right here? Quote the p-value, and is this difference large? So these mothers are perfectly identical right now. They have the same education, the same race, the same husband's race, the same father's age, all these different things. It's smoking currently, and one of them is not smoking. So one of them is currently smoking now, and one of them is never smoking. And the expected difference between them is how many pounds in their baby birth. The expected difference between them is how many pounds in their baby birth. Does it come back? Not pounds. Oof. Not pounds. That's not pounds. That's ounces. The expected difference between them in pounds is this, and still a good bit, right? And in ounces is this. So 8 ounces, Kayla. This is everything else is identical to you. We collected data on, what's your height, what's your weight, what's your age, what's your education. Great job, Alexander, right there. So 5.15 pounds, because 450 ounces in a pound. So that's a lot of grams. These are grams. So that's a kind of large difference right there. That's kind of a lot. And this is everything else identical between them. Two mothers who are otherwise identical. Kind of a bit of a difference. Q6 right here. Some suspicious baby. Oh, did we just do Q5? I think we did. Question 5. We'll put a guess on the timestamp. When talking about baby weight, that is a lot. That is very true. Weight 8 grams. No, not 8 grams. 8 ounces. 8 ounces. 8 ounces. Sorry, Kayla, I might have misspoke right there. It's 8 ounces. It's 0.5 pounds or 8 ounces or 232 grams. Those are all the units right there. 232 grams, 0.5 pounds, 8 ounces. Those are all the the units right there of measurement. There we go. And let's do some question 6. What time is it? 51:40. Thank you so much, everyone, for being here. There is some suspicion that that's very nice of you. Poorly educated women give birth to Who wrote this question? I didn't. The first line of code below shows that the difference in average birth weights between education levels is statistically significant. However, there is a statistically significant association between women's education and smoking, so we shouldn't simply compare birth weights of babies for each level of education without also accounting for the smoking habits of mothers. Use the drop 1. Now, this is going to be a very important conversation here on what drop 1 is. Determine if the variable mother's education is statistically significant in your model for Q5. Is there any difference in average birth weights between levels of education after accounting for the other information in the data set? So if you look right here, we have mother's education, and let's take a look right here. And so it wants us to use this model, I believe. So we have to know what the drop 1 is doing. Let's look at the summary of this model briefly and see something. How many, now be careful, I know, quite the mean question. How many levels of mother's education are there? Be careful. This is a trickier question than it looks to be. We have to make sure we know what's going on with the data. How many levels of mother education are there? How many levels of mother education are there? So how many levels of mother education are there? Be careful. There's not 4. Whenever you see this out, there's 3. Because what are you not seeing? There's 3. And why is there 3? Because what are you not seeing? Whenever you look at the output, what do you not see? You will not see a coefficient for the what? The reference level. Exactly. I'm trying to find a reference level output right here. So there's 2 levels to gender right here. Does that make sense? This output right here, there's 4 levels to weekday. Does that make sense? Because you see 3 of the levels here in the output. The 4th level, Friday, which is the reference level, is not seen. So when we look at this output right here, we see 2 levels, which means these are both the what's of the model. So we don't see the reference. These 2 are the what's, telling us this person has college, these people have high school, and we don't see the reference. These are the what's. Those are the indicators. Great work, Kayla. So these in Alexander too, these are the indicator variables. So the reference level is what we don't see. And this is what the question is pointing to. Look at both of these indicator variables. They're both positive, meaning that compared to mothers, and I think it was with no education, it said, compared to mothers with no education. Let me see here, mother education. I think the level is no education, really. Below high school is the level. So the below high school level is what we don't see. So 2 mothers who are otherwise identical, where one of them has education college and the other has below high school, the mother with college education is expected to have a baby that is 1.86 grams heavier. When a category just has 2 levels and the people that is correct, Alexander. That's a great knowledge thing right there. When it has 2 levels, we can just look at the one level, the one variable. But when it has 3 or more levels, I think you've been reading ahead in the notes. When it has 3 or more levels, you have to do the partial F. And that's what this question is alluding to. Because think about this. If we want to look at the impact of mother's education, and Alexander said it perfectly, we have to remove 2 things from the model. So to look at the impact of this, we have to look at 2 things removed from the model. I can run the drop 1 test right here, and I can tell you what the p-value of this is going to be before I do it. Would you like me to quote the p-value down to what it's going to say for the p-value on this, down to the number? You ready? The p-value for this is going to be 0.001434. Oh, what did you do? Test equals F? Really? And if you wonder what I just said right there, the p-value I was stating is this. The p-value of the model right now is comparing it to the naive. Alexander, does this make sense? And Kayla too, because Alexander, you were commenting on this. So that's why I'm kind of pointing the question right here. The p-value right here compares the reduction in sums of squared error of including both of these to the naive. This drop 1 removes both of them and compares it to a model with both of them removed, which is the naive. Does it make sense mechanically that these are doing the same thing? that this p-value right here is our model compared to the naive, where this p-value right here in the drop 1 removes one of the variables, which there's only one variable to remove. It removes all this and compares it to a model without that variable in it. How's everyone doing on that? It's a big concept. We're going to see it in more depth here in a moment. How are people doing with that concept? So the drop 1 takes out one variable from the model and compares it to a model without that variable. Now you might ask, why is that important if it just did the same thing? It's important because in the previous model, we had a much larger model. So now take a look. Oh, I didn't do test equals F. I'm losing my mind. Now take a look. I think, yes, those would be flat lines. Correct. And now, mother's race. Well, let me look. Let me show you the original output first. Here's the original output right here. In this output, if I want to remove mother's education, how many variables am I removing? If I want to remove mother's education, how many variables am I removing? It's that simple. It's not a trick question, I promise you. How many variables am I removing from the model if I want to look at mother's education? How many variables am I removing from the model if I want to look at mother's education? Just, it's as simple as it sounds. I'm not asking a trick question right here. How many components of the model am I removing if I remove mother's education? I promise, not a trick question. 2. Because it's those 2 things, right? So the problem is if we want to remove multiple things from a model, we need to do a what kind of test? If I want to remove multiple things, if I want to remove these 2 things right here, I can't just pull 2 things out of a model. If I want to remove 2 things, don't worry, Kayla, don't worry. What do I have to do if I want to remove 2 things? It's called a what F. So I want to compare a model without these 2 things to a model with these 2 things. So what is it called? It's called a something F, to compare a larger model to a smaller. Well, we're going to do partial models, right? Partial F. So now I'm saying, let's remove just those 2 things. Great job, Kayla and Alexander. Great work. But I want you to think about this, Alexander. And Kayla, sorry. If I want to remove smoking, how many do I need to remove? Promise, not trick questions here. How many do I need to remove if I want to look at smoking? To look at smoking, I need to remove how many things? Like if I want to say, what's the impact of smoking? How many variables do I need to remove to look at that? Careful. Well, not all of these at once. Kayla, that is correct. Just one. Now, I know I have 3 things circled, but let's say I'm like, is smoking impacting this model? Well, smoking is a 2-level categorical, which brings with it 1 indicator. So because the other one's the reference. Mother's race is a 3-level categorical, which inputs 2 indicators. Does that make the difference between these 2? This is the crux of this question, what we're trying to have you learn and understand here. So since smoking is just 1 indicator, exactly, because it's just the one, it's smoking now versus never, never being the reference level, now being the indicator. So I can tell you the p-value in the partial F. Does anyone know the p-value in the partial F? Oh, don't worry, we will be covering this in class, Kayla. The assignment will be due Wednesday, and I think I'm putting the activity due on Tuesday. I'm going to work a little more on the dates here, probably later tonight or something. Do you know the p-value for the partial F for smoking? Because it's going to look at a model with smoking removed. So the partial F is going to have a p-value for smoking of what? Which is the significance of the whole removal of the variable smoking. Kind of close to 0. Can you write it in scientific notation what the p-value will be? The p-value, since it's only 1 thing being removed, do you see it? The partial F's on the screen. Alexander, that's right. And why is it? Because we're just removing 1 thing. So this p-value down here is from the partial F. And so it's still just the same p-value because this is the p-value of a model with and without this variable. But mother's race, which is right here, we'll highlight it. No, mother's education we're doing. Mother's education has us remove how many things? Look at the value right here. Mother's education has us remove how many things? Mother's education has us removing how many again? See, smoking only had us remove 1. Mother's education had us remove 2. So the overall impact of those two was not statistically significant in the model. Does that make sense what this is telling us? 3 overall levels, exactly, because 3 levels makes 2 indicators. And so there's 3 levels total, 2 indicators in the model, and the indicators are what make predictions or, from the reference level. Is this making sense right here? How's it looking? Doing pretty good? But yeah, that's got the output right here. This tells us that mother's education does not bring with it new information as a variable as a whole. I do want to say one last thing on this. When you're looking at this output right here, the significance of this, because this is the summary, this is telling us if there's a significant difference with what? With education college versus education what level? That p-value is not the significance of mother's education. That p-value is the significance of mother's education college level, and if it is significantly different from what? So that p-value right there is not the significance of mother's education. That's the significant difference between mother's education college level and how different it is from the reference. Exactly. Where down here, there's only one line in the reference, so the literal whole variable is that. So down here with one indicator, this is the model. Like that's why that p-value is the p-value. Does that make sense theoretically? This p-value is the p-value because the significance is just this one difference. These 2 lines difference is the model, and that's the significance. Where up here, there would be 3 lines and the reference level. So all of these coefficients right here calculated are significant difference from that line. So you need an overall removal of this via the partial F test, which is done via the drop 1. Lots of big words, and we will be reviewing this next week. This is the end of the lecture. But good work. Tell me if it's not making sense. Check regression, our old friend. Get ready. Life gets easier here. I promise you. You're like, no, Brian, I know when you say life gets easier, it never gets easier. Look at the model from Q5. That's the crazy model, right? So let's go here to check regression. Once x equals true. Ooh. I don't know. I got an extra. Whoa. What do you notice? I mean, I'm happy. This is good. Let's see what we got p-value wise. Okay. Where are there issues? I mean, overall, this is pretty good. So it can't run check regression on these. But where are there issues? How many issues are there in this regression? 0 through 50. Got to get my awesome. Give what they weighed. No, but great job, Kayla. Great work. The normality of the residuals, that is correct. And where else? So the normality of the residuals, there is an issue with that. Let's go look at that. Boop. Here it is over here. I'm perfectly okay with that. That is fine. That's cool. Then where else do we see issues? There's one more issue on the screen. There's one more issue. One more issue. And we are going to have to run additional code. So let me get the code ready here. There is an issue. The linear relationship. Great job, Kayla. Kayla said you're going to run away. Don't worry. Hang out. So the answer is... I don't see it. I don't see it. It says there's not a linear relationship there. Whatever. I don't see it. It's fine. That's the only one we need to look at. Remember, low p-value. Bye, Kayla. Low p-value means there's an issue with that variable. So, yeah, I don't see it. I don't see it. Influence plot to see if there's influential. Baby 553 is influential. It's in Baby 553 is an influencer. You didn't know it on the full model, Q5. Okay. Wait, I did influence. Let's find out about this influencer baby. Woo! Okay. So, we got the next question. Let me mark it. Question 7. We're on question 8. Check regression. Okay. Question 7. 106, 10, 15. Okay. So it's important to know what this output is showing us right here. In this output, Leverage means something is unusual in the X space. A baby down here is one that is as average could be. It's your average baby. Now, you might think it's over here, like at this line. This is when something starts to have high leverage. So these babies over here have too much leverage. They're too unusual in their X combination. But you can be unusual in your X combination, like this is a very unusual baby, but you could be near where the model predicts you. This baby does not have a large deleted studentized residual. Deleted means we remove out the impact of the variable from the model, so we delete it. It'd be gone. And then studentized means we've standardized it, basically. These are t-scores, not z's, but you can think of them as z's. So things outside of 2 and -2 are unusual. More unusual, z-scores or t-scores technically further away. And residual is your classic actual minus predicted, telling us how far these things are away from the model. So in the very kind of concise sense, this is how far they are away from the model with their removed impact in a standardized value. And so there's a very extreme baby there with a very bad prediction from our model, as is there. That's 1, 2, 3, 4. And there's 4 because there's the row numbers of them. Let's go investigate and find out what is up with that one. In a studentized residual, it's the residual with the point removed. Studentized means it's a t-score, but deleted. A key word right there, Alexander, would be deleted studentized residual. And what is it? There's a regression. We have a way of doing it. What it would look like, I'm going to do a quick sheet of paper. So if you have data points that look like this, and then you have an extreme point down here, the extreme point will pull the line towards it, but the model without it would look like this. So this in pink is the residual. And then in yellow is the deleted residual. Does that make sense there, Alexander? That it's the gap between it. Yeah, exactly. Because the black line is with its influence removed, and then studentized means it's been turned into a t-score, so it's standardized units. So deleted studentized residual means you literally delete the point itself, and then you create a model without the point. Of course, you need the point to figure out. So the point has no influence because extreme points, things that are far away, will pull the model towards them. So rather than letting it pull the model towards it, i.e. reducing its residual, which we can see right here, the residual will always be, it's a good theory question, and studentized is just how unusual it is. Exactly. So then we can just say, oh, it has a deleted studentized residual of 10. Would you say that's pretty large? Like if someone told me that has a deleted studentized residual, and it would have to be of -10. It can't, because it's below the line, so it'd have to be -10. If I told you that was -10, you'd say ridiculous. And the reason is because it's basically z-scores, and a z-score of -10 is like ridiculous. It'd be off the scale. That's not even perspective accurate. It would be like the normal curve here, and then we're 1, 2, 3, 4, 5. We're way down here. It's way off the curve. 10 standard deviations below what we would have expected. And technically, I guess it's standard errors, but if it's that far away, it's an extreme point. And so that's what we're looking at right here with this output, is a studentized t-score value of how far an observation is away, and then the leverage is how far odd it is in the x-axis. So we can look at just this one baby right here, find out what's weird about them. Here they are. Oof. Their birth weight is very low, but that's a y variable. But their mother had a very short pregnancy. Their mother is a little bit older. The mother's 5'5", the mother's 140, the father's 36, the father's a little bit heavier. To me, what seems most unusual is that the mother, this gestation period, I think, is the shortest gestation period. So she's very unusual right here. And probably, let me do one last comment on this. I think that the mother didn't smoke. Oh, and she didn't smoke. Oh, and that's unusual too, because you'd expect her to have a lighter baby if she didn't smoke. Figure too large. This might be too much. It's going to be too much. We'll let that go. Whoa! That's when you make a thing too big. Part B, load in the tips data set. Let us investigate whether... Wait, part B? Sure, part B. Part B. We'll just put part B in here. 25. Part B. Let's learn the tips data set, investigate whether there's a difference between the average tip percentages between smokers and non-smokers. Smoking is the name of the game today. And so let's load in. We got tips loaded in. Tips has the variable smoker. And we want to look at, is it tips or tip percentage? So tip percentage smoker, comma, data equals tips. And there we go. And let's look to see if there's a difference right here. And how are smoke? Ooh, good news for those who wait tables. It looks to me that there's not much of a difference right here. There's not a statistically significant difference. Yeah, so there's not a statistically significant difference between those who smoke and their tip percentage. Notice here that the average tip percentage is 15.93. There's a difference of 0.38, where people who smoke are likely to tip higher. Like two individuals who are otherwise identical, where one smokes and one doesn't. The person who smokes is expected to have a tip percentage that is 0.3884 higher percent than the non-smoker, but this is a non-significant difference, likely due to random chance. Q2, sorry. Can I slow down? It may be that the case that association between is apparently accounted for by Bill. Okay. Fit a model predicting Bill and smoker in the model. Okay. Let's go down here. And let's add Bill to the model. And a little more significant, but not really. These lines are going to be kind of close together. The lines are going to differ by 0.75. So we're going to see a red and black line kind of close together. People with higher bills tend to do a lower tip percentage. We can see that. Two bills that are otherwise identical but differ in the bill amount by $1, the higher bill is expected to have a lower tip percentage by $0.23, by 0.23% tip percent. This is in tip percent. But also the coefficient right here, which is not statistically significant, would suggest two bills that are otherwise identical, where one is a person who is smoking yes and a person who's smoking no, where the coefficient's positive. The person who is smoking yes is expected to have a tip percentage that is 0.75 higher than the non-smoker. Now we get into the really interesting stuff. Part B, from all the variables in the data set, account for all the information. By how much is the difference, and is the difference statistically significant? So we're going to go over here and do the same thing. Take our model, and let's do a summary of it. And smoking is, wow, it is statistically significant. And whoa. And Alexander, this is the thing. This is the thing. You can never tell if something is going to be significant in the multiple world versus the simple world, because with the other variables in the model, this variable brings with it new information that the other variables are not accounting for. It's actually one of the few. Tip and bill are very significant, but there's a lot of not significant variables in the model. But smoking now brings with it in this model new information not accounted for, where by itself and in the previous model, smoking did not bring new information. So it went from being not significant by itself and in a multiple model to, in this model right here, smoking does bring with it significant information unaccounted for by the other variables. In two individuals who are otherwise identical, where one individual is waiting on someone who's smoking versus someone who's waiting on someone who's not smoking, the person who's waiting on someone who's smoking is expected to get a tip percentage that is 1.65% higher. It would have the R squared adjusted. So the R squared adjusted will go down if we add variables that shouldn't be added. The R squared has gone up. Adding more X's will always increase R squared adjusted. So R squared, wow. I got to get some food. Adding more X's will always increase R squared. R squared adjusted is adjusted for the amount of variables in the model. Does that make sense, Alexander? R squared adjusted is adjusted for more variables in the model, more penalty on the R squared. Now, R squared adjusted can go up, but when we needlessly add X's to the model, R squared adjusted will go down. And really quickly, what you often want to look at, a little sneak peek right here, is you want to look at, I cannot run AIC on that. There's the AIC, the Akaike information criteria on this model. You can compare that too, but we haven't mentioned that yet. What's the R value when comparing all the variables to one variable? So if you want to compare like models to models, which one should you compare? Like what in this output would be used to compare models to models? Should you use R squared to compare models to models, or what would you use to compare models to models? to compare models to models. And you might be thinking, I think you might be thinking R squared sub I, which is the R squared of the ith x in your model. R squared adjusted to compare models to models. R squared adjusted compares models to models because it's a fair comparison because it's adjusted for how many variables in the model. R squared sub I is the R squared of the ith variable in your model used to find variance inflation via over 1 minus R squared sub I. So the R squared sub I, exactly. And so I thought, I was like, I think you're remembering another topic, and that is the R squared of the ith variable in the model. When you make a model where your x is explained by your other x's, it doesn't quite look like that, but the x is the variable of interest in that model. So we call it R squared sub I for the ith x. And so it's a specific kind of R squared that we don't want to be high. And oh, that's what you're alluding to. You don't want your R squared sub I to be high. You want this to be high. You want this to be high. You don't want your R squared sub I to be high. That's a good theory question about which R squared do you not want to be high. Exactly. And that'll give us a metric of how much variation in one x is explained by the other, which is a metric of correlation, multicollinearity between multiple x's. Great work, Alexander. Let's see. R squared. Yeah, low R squared sub I is good. And that'll lead to a low variance inflation factor. Good. Fit a model predicting bill, not tippers. Oh, predicting, okay. From party size and weekday obtained in the summary and write out the implicit equations for Friday and Thursday. Round the coefficients. Okay. M save into LM bill party size plus weekday data equals tips. Okay. And anytime we do this, we're going to do the following. We go right here and we write out, we're predicting bill equals this plus this. Now what we can do, we're going to do the shorthand version of this. Alexander, you were saying it earlier. What is the only thing that changes between these models? And here we can show it visually. The only thing that changes between these models, I'm going to visualize that model. The only thing that changes between these models is the what. So look at the models over here, and the only thing that'll change is the what between these models. So here is just the base of it right here, and then the only differences right here are differences in the what value, which you can see visually over here. Because we're going to plug in zeros or ones for these, you can't plug in ones for multiple. The y-intercept, exactly. So this is actually right now, because we didn't include anything else, this is actually the what line right now, Alexander. Because this is a 0, this is a 0, this is a 0. And so this is the information I've included in it. Not that. This is actually the what line currently. Because I didn't turn on any of the indicators. You could call it by its name. It's the Friday line, which is the reference. Great job, Alexander. That's the Friday line, which is the reference. So if we want to do a shorthand way of doing this, we could actually go here and we could take, because it said Thursday, and subtract this from the intercept. And the value of the Thursday intercept is this. So all we did was subtract from the intercept that, and now we have the Thursday line, which is just below Friday. You notice how Thursday is the lowest and Friday is right here. There are lines above Friday, which are Saturday and Sunday. Sunday is basically overlapping Friday right there. And you can see it right here, how Sunday has just a tiny positive coefficient and Saturday has the real positive coefficient, as seen in the output, where Saturday is about a unit higher than Friday. Good stuff. Among equally sized party was the difference in average bill between Sunday and Friday. So Sunday and Friday is this, which is about nothing. How about Thursday and Saturday, though? This is where I talk about my family, because if we have Thursday is a negative and Saturday is a positive, well, we can actually take and subtract their differences. Be careful, though, because when you subtract a negative, you're actually adding it. Great job, Alexander. Another 100 points. That's a common mistake that I mentioned right there, that people don't realize that you're kind of going through it. It's basically make sure you're going through zero, so you're actually subtracting a negative is actually adding it. So be very careful on that. I've seen a lot of people say, well, the difference is only like 0.4, and I'm like, but that's 1 and that's -1, so it's at least -2 or 2. After accounting for size of party, on which day is the average bill the largest? The average bill would be the largest on Saturday, and Thursday it would be the smallest. among equally sized parties is the difference in average bill statistically significant. So the drop one is actually doing a what again, Alexander? And I'm going to show one last thing right here. I have to do one last additional thing on this to make sure we know all topics. The drop one is actually doing a partial F. So it's going to take all of those. So how many coefficients or how many variables will the partial F look at here? The drop one. How many X's will it look at? So it's going to bundle everything up and drop things that have multiple levels together. Close. Well, I think that's the right answer for, maybe I didn't phrase it well enough. It's going to drop all three of these. And so that's going to become the variable weekday, and that's going to be removed from the model. And then it's also going to look at party size. So when we run the drop one with test equals F, I actually did it before it asked me to, we're going to see two variables here. It's going to bundle up those three, like you said, and that's going to become the variable weekday, and it's bundled. And we also see the previous variable that we already knew the p-value for, which still just has the same, can I get it on the screen? Still just has the same p-value up here. So the p-value for that is still the same because it's just the same variable removed. But the last thing we have to know, which is where things get tricky again, is when it comes to these models, we could have interactions. And when you have interactions, it doesn't just change the intercept of the model, right? The word, when you have, exactly, great job, Alexander, there. If you have interactions, it doesn't just change the intercept, it would also change the what of the model. If you have interactions, it wouldn't just change the intercept of the lines. The interaction would allow for differences in what's of the line. So take a look. No interaction, interaction. No interaction, the indicators have different intercepts. Interaction, they have different intercepts, and they have different what's. So if there's no interaction, they just have different intercepts in their parallel lines. If there is an interaction, it allows for them to have different intercepts along with different what's. Slopes, exactly. So allowing an interaction on an indicator variable allows for each line to have its own unique slope. And the way you would calculate the model here, it looks like a lot of output. But the interactions right here are just differences in the what's of the line. So each interaction term, we could write our base model again. So we're predicting Bill. Bill equals this. Oh, it's negative. Then we get the party size. So, oops. So now that we have this is actually the Friday line, because the Friday line is the reference. But if we want to calculate Saturday's line, look at Saturday compared to Friday. Saturday's slope is what compared to Friday? So just look at Saturday the black, or Friday the black line, and Saturday the green line. Saturday's slope is more, less, or the same as Friday. So there's Friday the black line and Saturday the green line behind me. Wow. Sure, Saturday. Saturday works. Sunday's the green line. They're all less than. And since they're all less than, every one of them is less than, all of the interactions on party size are negative. And it works the same way, where we just plug in a 0 or 1 for here, and then we would reduce, and you would have party size times this, which is going to change the party size coefficient. So if we want to write, and they're all negative, exactly. And if you look at the coefficients of the interactions, all the interactions are negative because all the lines have a less slope. So if we said, which day has the strongest relationship? Exactly. And they reduce the party size. Yes. When you see it, it's like, oh, that's all it's doing. And you just solve it mathematically. So if you want to solve for Sunday, you'd go here and you would add this to the intercept. Now, remember, the intercept is negative, so we're just going to subtract that. And this is the new intercept. It's positive now. And we're solving for Sunday, I think we said. Yep. So now we go down here to Sunday, and Sunday's going to change the coefficient of the slope by this much. So we're going to take our coefficient of the slope. Oh, did I just paste over that? I think I did. There we go. We're going to take that, subtract from it this, and this is the new slope. And that is the Sunday line. Friday would have the strongest relationship. Exactly. So there's test questions that say like which one has the strongest relationship, and it's because all other slopes are weaker than Friday. And does this make sense, Alexander? How I wrote the equation for Sunday by subtracting the intercept by putting in the indicator Sunday, because this value right here is the difference between intercepts, i.e., it went from -2 to 8 because we added it. And then the party size went from 9, it was 9, and then we subtracted from it the 4.5, making it 4.7 because it was 9 and we subtracted because it's less. It was higher and then we subtracted it. Does that make sense? These are some of the harder questions, and the interaction is actually not statistically significant. That is actually the drop 1 done for you. So it'll actually do the drop 1 in the visualization of it. So there is, I gotta do a test F. I had almost learned to do it. And so the visualization actually gives you that. There it is right there. And there's the p-value. It is the reduction. Yep, exactly. I think you're getting right there. Exactly. And the interaction does not bring with it new significance. And interestingly enough, variance inflation is usually an issue. Yeah. So when it comes to interactions are created from variables. So the variance inflation here is crazy. Because the interaction is created from it. So it contains the information from the variable. So it's a little bit redundant. And there's just very high multicollinearity here. Like we could make a model with just the interaction, which is ridiculous. It'd probably be significant, I'm guessing. But that is ridiculous multicollinearity. I like messing with models. Let's see. Yeah, the interaction itself is significant, but probably due to the multicollinearity, literally. I don't know why it doesn't default to this. Yeah, it's high redundancy. So we probably want to look at the AIC. AIC is model's closeness to truth, or look at R-squared adjusted, or look at RMSE. A lot of good ways to measure it, but that's got it. Alexander, great work. Whew. I'm going to go. Test has been open for 20 minutes. Hopefully things aren't too crazy. I'm going to let you go. Excellent work, Alexander. Keep up the great work. We'll be back here after Easter, after spring recess. Bye for now, everyone. Bye, Alexander. Bye, Caleb. Bye, Nick. Great job, Nick. Bye, bye, bye.
Happy spring recess!
You too, Alexander.